If I told you that training a language model for too long actually makes it dumber, would you believe me? It sounds backwards. More compute equals worse performance? That's like saying running more laps makes you less fit. But this week in AI research, we got proof that training isn't a straight line, it's a curve that can bend backwards and bite you. And that's just one of the bombshells that dropped this week. Welcome back. This is your Week 22 briefing on LLM training and scaling laws, and trust me, you need to hear this. Let's start with the weirdest result first. A researcher named Chuo Yang dropped the Shannon scaling law. Training an LLM is like sending a message across a noisy radio channel. Every channel has a maximum information capacity, a hard ceiling. Push more bits through, and you don't get more signal. You get distortion. Yang proved this happens during LLM training. Overtrain a model, push too many tokens through, and performance doesn't plateau. It degrades. Same with quantization. You'd think more training is better and compression is fine, but Shannon says no. The math holds up. They fit models up to 6.9b parameters, then predicted unseen 12b models with R² equals 0.8 for 7. Why does this matter? Because the entire industry assumes you can always train more, compress more, push harder. This paper says you can't. There is a Shannon limit. And if you ignore it, you're actively making your models worse while burning GPUs. Next up, the mixture of experts headache that everyone has been quietly suffering from. If you've been following AI, you know MO is everywhere, GPT-4, Mixtral, DeepSeek. The idea is you have a bunch of smaller expert subnetworks and a router that decides which experts to use per token. It's efficient. It scales well. But it's a nightmare to tune. Hyperparameters that work for a dense model don't transfer to an MO. So researchers have been retuning from scratch every time. That's expensive. That's wasteful. Enter Complete-muE from Hongwu Peng. This paper builds a mathematical bridge between dense feed-forward networks and any MO variant. They use something called active width parameterization, which is a fancy way of saying they figured out how to map hyperparameters from one architecture to another with high precision. The result, tune once on a dense model. Transfer to every MO variant you want. Done. This is a practical breakthrough. It means faster iteration cycles, cheaper experiments, and less blind guessing when launching new MO models. If you're training LLMs at scale, this saves you weeks per experiment cycle. Here's a scenario for you: you've trained a model, but something's off. It's great at code but bad at reasoning. Or it hallucinates medical facts. You want to know what went wrong in the data mix, but you don't have access to the original training data. Maybe it's proprietary. Maybe you inherited the model from another team. Maybe you downloaded an open-weight model and have no idea what went into it. What do you do? LLMSurgeon by Yaxin Luo solves this exactly. It's a post-hoc auditing tool that looks only at the generated text from your model and reconstructs what domain mixture the training data had. It treats data mixture surgery as an inverse problem, like working backward from a fingerprint to identify who left it. The fidelity is remarkably high. This means you can now audit pre-training data mixtures without needing the original dataset. For compliance, for debugging, for understanding why a model behaves a certain way, this is huge. What if I told you there's a way to get plus 2.6 for points on MMLU-Pro with zero additional training? Training free loop transformers from Lizhang Chen does exactly this. You take a contiguous block of layers from the middle of your model, doesn't matter if it's dense, MO, or even the new multi-head latent attention plus MO combo, and you just loop it multiple times during inference. No fine-tuning. No gradient updates. Just run the same block twice, 3 times, and the model gets smarter. They tested it on Qwen 3-4B and it jumped plus 2.64 percentage points on one of the hardest reasoning benchmarks out there. This works because reasoning benefits from recurrence. The model gets to think longer by reprocessing through the same computation. And because it's a mid-stack block, you're not double counting the embedding or output layers. Smart, elegant, and completely free at inference time if you can afford a bit more latency. Distillation, using a big teacher model to train a smaller student model, is a standard technique. Conventional wisdom says, use the biggest, most capable teacher you can find. More knowledge to transfer, right? Wrong. MMLU discovered that small, undertrained teachers consistently produce better students than fully trained, powerful ones. Stronger teachers hit a saturation point, and beyond that, they actually make the student worse. Why? The researchers hypothesize that overly capable teachers produce output distributions that are too sharp, too confident. The student copies the overconfidence and loses the exploratory behavior that helps it generalize. A weaker, softer teacher gives the student room to learn. This flips a core assumption of knowledge distillation. If you're running distillation pipelines, you might be using teachers that are too good. Finally, 2 papers on data organization that deserve attention. Microsoft's STR and SOR ordering methods show that simply rearranging the order of training data can match full corpus performance using only half the tokens. That's a 2x efficiency gain from ordering alone. No new data. No bigger model. Just smarter sequencing. And MIRA, mid-training rubric anchoring, gives you a way to do source-aware data selection during training. It anchors the selection criteria to a rubric that adapts mid-training, so you're not stuck with a static data filter that becomes obsolete as the model learns. Together, these papers say data quality and data organization are at least as important as data quantity. We've been drowning in more tokens, but maybe we just need to arrange the ones we have better. Let me tie this together. This week gave us a theoretical ceiling on how far training can go, the Shannon limit. A practical bridge for MO tuning, no more